Okay, so I want to just like end this lecture or end the topic by discussing the density operator or the density matrix. So let me recap probability in quantum mechanics. We said that, if I have some state and I, express the state as a linear combination of, say, some eigenstate of some operator, it could be, say, energy, for example. So blah, blah. And these are eigenstates of, say, energy E1, eigenstates of energy E2, stuff like that. Now, if I know that this is the state of my system, and I want to measure the energy, that is the Hamiltonian, then the possible results that I'm going to get, the possible results will be one of the eigenvalues, E1, E2, dot, 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 whatever, right? But what are the probabilities? The probabilities are C1 squared. If I assume that it's normalized, that this thing is normalized, C2 squared, dot, dot, dot. If it's not normalized, then these are all relative probabilities, which is fine too. So this is the probabilistic interpretation, and this is the Born interpretation in some sense. Well, it is the Born interpretation. But there's another kind of probability in quantum mechanics that people are not taught in their undergraduate physics for some strange reason. I was not taught. I learned it very, very late in life. And the idea is something like this. Suppose you have a collection of states, psi1, psi2, psi3, and you have multiple copies of this. And this is some box. And inside the box is a daemon, is a descendant of Maxwell's daemon or something, although it's not a paradox. And the box has kind of a little opening, and you can't really see what's happening inside the box. And what happens is that once in a while, this daemon has a die, some multi-sided die with some weird probability distribution that we don't care about. And every often, in what happens is that the daemon, sends out once in a while a state. He sends out state psi1 with probability P1. He sends out state psi2 with probability P2, and so on and so forth. It turns out that this condition, how do you describe the situation? You are now doing an experiment, and you want to write what is coming out as one state. You do all these experiments, you measure the states, you build up the probability distribution. How do you don't know what the daemon is doing, how do you describe the situation? It turns out that situation cannot be described using this linear combination technique. And that's something that I'm going to put in a tutorial problem to show that it cannot be expressed like that. To express this more general sort of situation, we need something called a density matrix. Okay? So what is a density matrix? Where did my... Here. So density matrix is, so suppose we have a collection of states, psi1, psi2, dot, 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 say psi n, each with the probabilities P1, P2, dot, dot, Pn. These are the probabilities of these states getting chosen. Then the state of the system is described by a matrix which is sum of Pi, the probabilities, times the ket times the bra. Okay, so this is a matrix. And you might say, oh, how is this a matrix? Let's take an example. So if I take my ket, say, to be some two-dimensional vector C1, C2, then what is the bra? This guy is going to be C1 star, C2 star, right? And then if I consider not the bracket, but the ket bra, which is this thing times this thing, what I am doing is that I'm taking an outer product. That is C1, C2 times C1 star, C2 star. This is not the usual matrix multiplication. This is the outer product. And then if I multiply these two things, what do I get? I get C1, C1 star, C1, C2 star, C2, C1 star, C2, C2 star. So I get a matrix, a 2x2 matrix. So we see that, if our Hilbert space is n-dimensional, then this matrix is n by n dimensional. And if our Hilbert space is infinite dimensional, it's an infinite by infinite dimensional matrix. So this is the definition of a density matrix for a discrete finite dimensional case. The definition of a density matrix for an infinite dimensional Hilbert space is given by sum over I, pi, psi I of x, psi I star of x prime. Okay. So we will finish this off in the next lecture. I think this is a good place to stop and take the attendance. And then ask some questions. Okay, I have run out of attendance on my Excel sheet, so I'm going to create a new column. Insert. I have forgotten Excel, it seems. No. Okay. Entire column. Okay. All right. So, do we have Samiha?
Yes, sir.
Okay. Afia? Wajiha? Okay. Rahul is here. Moon?
Yes, sir.
Awesome. Zabir?
Yes, sir. Amen.
Awesome. Nafis?
Yes, sir, I'm present.
Nusaiba?
She is present, but her mic is not working.
Okay. I gave her I gave her the attendance. So, Dipro?
Present, sir.
Awesome. Medat? Yeshan?
Present, sir.
Shujosh?
Yes, sir.
Shitima?
Present.
Awesome. Abdullah? Muhammad Abdullah? You're here,
Yes,
right?
sir.
Yeah. Nahi is here. He asked a question. And then Saif, you're here, right?
Yes, sir.
Nian is here. Okay. And then Abdullah Al-Rafi Mahmoud.
Yes, sir.
Abdullah Al-Rafi Mahmoud, what do I call you?
Sir, you can call me Rafi or Mahmoud,
Okay.
whatever you like.
Okay. All right, Rafi. And then Farhan is here. And Oshik. All right. Thank you. So now,
Sir,
anyone can leave if you want to, but but those of you who want to ask questions, I'll be here for a few more minutes.
So did you mark as present for Nazmun Falguni Moon?
Yes, I did.
Okay, her Wi-Fi is poor, so she
Oh
told
no,
me.
I didn't. That's a very good idea. That's a very good thing. Thank you. Yeah. Okay. Okay. I see. Okay. And I have so many like yeah. I think they. Okay.
So on the last class,
The
she was
cyber is
present.
there. Yeah. Well,
So
she was
Moon
present.
was
Okay.
Moon was present on the last class as well, but I don't know if you
Yeah,
marked her.
she is marked present on the last
Okay,
class. So
thank
yeah.
you, sir.
Okay, good. All right. Any more questions that I can?
Yes, sir. Like, I didn't like get why were we trying to motivate the density operator in the first place? Like, what we able to do without it?
Right. So that's a very good question because density operator is, yeah, you'll do it. You'll do that problem much more. You'll do actually a concrete problem in the tutorial. But for example, my question is, can you model this situation? Like, can you model this using, this mathematical structure? I can prove that you can't.
Oh,
Okay.
I see.
The statistics that you get from here, just think in a simple terms. Just think of upstate and downstate. Okay, suppose that the daemon had only upstates and downstates. And the daemon was doing 50, 50. Okay? So how would you model that? Can you model that using this? Do you think you can? So one thing you might try is the thing you would want to try is this, right? This is going to be okay. This is one
Square root of 2.
yeah, 1 over square root of 2 of this plus 1 over square root of 2 of this, right?
Mhm.
And if you're doing FZ, you would say, yeah, it gives 50%. But now if you do S of X, you will find that this will give you this will not give you 50%. But if you express this in the X basis, then you will still get 50%. You can work that out. So this thing does not work. It works for if you're measuring SZ, but as soon as you start measuring SX or SY, you get a result different from this. Okay? So that's so go and work this out, Mahi. This will also be a tutorial problem.
I think the place where I was really confused is the fact that the daemon, so it has to be an autonomous daemon, and I really can't relate.
Well,
to
daemon doesn't matter because it's really the die that is doing the job. The idea is that we don't know what this there is some pure state, but we don't know what the pure state is being chosen. It is being chosen according to some probability distribution, which we know, which we have measured out, but we don't know. So this is one thing. Another thing is that it could be so in statistical mechanics, what's going to happen is that if I have a system whose energies are given by En or En, so we have got states n and En, then the density matrix is going to be simply given by sum over n, and then the outer product. But the probability here is just the Boltzmann factor. This is something you saw, but you saw it in the classical context, right? So this is the canonical ensemble for quantum systems, and this is a density matrix. This is not, because this has exactly this form, right? This has exactly this form, where we are normalizing the probability by dividing by this, right? I mean, this thing is just Pn.